friends, as our discussion is ongoing on lecture number 8th and we have reached up to the part 3rd of 8th lecture, as I have mentioned here that these topics are the major topics of discussion of this lecture. So in this lecture we will be discussing mainly about Michaelis Menten equation, the significance of Km and Kcat values in enzyme kinetics. I would like to highlight this point because in many competitive exams as well as many other UG and PG exams, enzyme kinetics is a favorite topic of examiners to set question on them. So it's my request to you to please keep your pencil and a notebook because we will be solving some steps in the reactions. There are maybe 11 steps in reactions, so I have made them easy to understand you. So please focus on these steps and ask me if any query is there in your comment section. So let's begin our lecture, part 3rd.
Hello friends. In our discussion about enzymes, we have reached to the topic of enzyme kinetics, which is very essential topic. In basic chemistry, we know that first order reactions in which the concentration of reactant, in this case we can consider reactant as substrate, give rise to the product. And in second order reaction where two reactants give rise to the product, means the first order and second order reaction are dependent upon the concentration of reactants. But when the reaction is independent on the concentration of reactants, where in enzyme catalyzed reaction cases, these reactions are known as zero order reactions. Here we are talking about enzyme kinetics. So you must know what is word kinetic means. Kinetic means speed or velocity of reaction, and enzyme kinetic means velocity of reaction which are catalyzed by enzymes. To understand this, we will be using reaction rate constant terminology. So which are these reaction rate constants? Let's see. We know enzyme binds to the substrate and which will result into the enzyme substrate complex formation. So for this purpose, the rate constant is used as K1, which is depicted here. Once this enzyme substrate complex forms, it has two fates. Either it will be go back into the separate enzyme and separate substrate, which is shown by rate constant K-1, or that enzyme substrate complex will result into the product formation as enzyme plus product, which is represented by rate constant K2. Always product formation is the main aim of that reaction. So the product formation is dependent on K2 rate constant. Here we have seen that. Hence the velocity of reaction is nothing but the multiplication or product of K2 into enzyme substrate concentration, which is very important equation, and we will be representing this as equation number 1. So let's discuss more about the values of enzyme substrate concentration in terms of steady state assumptions. So what are these steady state assumptions? Which are nothing but the formation of enzyme substrate complex equal to the breakdown of enzyme substrate complex, which is very important. I would request you to please understand this. On these concepts, many questions can be designed in competitive exams. We will see them in the end of the lecture, how questions are asked on these topics. So first understand here, we are using symbol of these types of brackets which indicates the concentration. So formation of enzyme substrate complex concentration equals to the breakdown of that enzyme substrate complex concentration, which is nothing but steady state assumption we are talking about. In the beginning, which reaction rate constant we have used for formation of enzyme substrate complex, which is K1. So we can write this steady state assumption in other word as K1 into enzyme concentration into substrate concentration. Into means multiplication, which are represented by dots. Because there are two possibilities of breakdown of enzyme substrate complex concentration, we can write K minus 1 enzyme substrate complex concentration plus K2 into enzyme substrate complex concentration. This will be our equation number 2, where we are talking about the formation of enzyme substrate complex concentration and breakdown of enzyme substrate complex concentration. So we can rewrite our second equation in following manner. At left hand side we are talking about formation of enzyme substrate complex using rate constant K1. That's why K1 into enzyme concentration into substrate concentration. And on right hand side we are using rate constant K minus 1 plus K2 in bracket, which is multiplied by enzyme substrate complex concentration. After making rearrangement in equation number 2, we will get equation third as at left hand side we have enzyme concentration into substrate concentration divided by the enzyme substrate complex concentration, which is equal to the K minus 1 plus K2 divided by K1. Remember, K minus 1 and K2 talks about the breakdown of enzyme substrate complex, and K1 talks about the formation of enzyme substrate complex. These photographs are for Michaelis and Menten, who have exclusively studied about enzyme kinetics and given an equation which is Km equals to K minus 1 plus K2 divided by K1, which is our fourth equation. So by putting our fourth equation into the third equation, we will get enzyme concentration into substrate concentration divided by enzyme substrate complex concentration equal to Km. And by making some rearrangement, by shifting the position of enzyme substrate complex concentration, you will see the enzyme substrate complex concentration equal to the enzyme concentration into substrate concentration divided by Km value, which is our equation number 5, which is very important. One thing we know, the substrate concentration is always and must be much higher than enzyme concentration. So the total enzyme, which is represented as ET, if we find the enzymes which are involved in enzyme substrate complex, and if you minus these enzyme substrate complex from total enzyme, we will get the free enzyme concentration. So our free enzyme concentration equal to the total enzyme minus the enzymes in enzyme substrate complex, which is our equation number 6. So after substituting our equation number 6 in equation number 5, we will find the enzyme substrate complex equal to, in bracket, total enzyme minus enzyme substrate complex, bracket close, multiplied by substrate concentration and divided by the Km, which is our now equation number 7. We are solving our equation in step by step manner. Each equation is dependent on previous equation, and after solving that equation number 7, we will get enzyme substrate complex concentration equals to the total enzyme concentration in numerator substrate concentration divided by substrate concentration plus Km, which is our equation number 8. So we have reached up to the equation number 8, and by putting our 8th equation in first equation, which was the first equation? Yes, V means velocity equal to the K2 into enzyme substrate complex concentration, and we were talking about finding the values of enzyme substrate complex, and now in equation 8 we have got that value. Now it's easy that putting 8th equation into the first equation will show velocity equal to the K2 total enzyme concentration, and at the numerator substrate concentration divided by again substrate concentration plus Km, which is our equation number 9. So friends, when all enzymes are involved in formation of enzyme substrate complex, means there are no free enzymes available now. When total enzyme concentration is equal to the enzyme substrate complex concentration, then it is obvious that velocity or speed of that reaction will be the highest or maximum, and now we can write it as Vmax or velocity which is maximum is equal to the K2 into total enzyme concentration. Why? Because already we have said that all enzymes are involved in enzyme substrate complex. This will be our another equation number 10. So if you substitute our equation number 10 into the equation 9, where it is said that Vmax is equal to K2 into total enzyme concentration, then we will get V0 is equal to Vmax into at numerator substrate concentration divided by substrate concentration plus Km, which will be our equation number 11, and this equation is known as Michaelis Menten equation for enzyme kinetics. So let's discuss about the features of Michaelis Menten equation in enzyme kinetics, where it talks about the assumption of enzyme substrate complex concentration. The second feature is enzyme substrate is in equilibrium with free enzymes concentration. The third assumption is the breakdown of enzyme substrate to the product is slow process. The fourth assumption is the enzyme substrate complex will result into the formation of free enzyme and free product, and that free enzyme will again go back to catalyze the another substrate. Michaelis Menten equation also gives a hyperbolic graph which shows, as shown here, x and y axis, where x axis shows the substrate concentration and y axis indicates the velocity of that reaction or speed of that reaction, which indicates as we increases the substrate concentration, the velocity of reaction increases. But at certain point, the increasing in substrate concentration will have no effect on the velocity of reaction. It is a plateau form, which we call it as velocity maximum or Vmax. But the substrate concentration where the velocity is half achieved, the substrate concentration where half velocity is attained, that substrate concentration is depicted as Km value of that reaction. Km value represents the substrate concentration. So Km gives an idea about requirement of substrate concentration to reach the velocity up to the 1/2 of the Vmax. Km is also useful to give an idea. Suppose in left hand side we have drawn one hyperbolic plot, and on the right hand side also we have drawn another hyperbolic plot. What is difference in between these plots? You can notice here at left hand side the Km value is more as compared to the right hand side. The more Km value to reach to the 1/2 of Vmax at left hand side, and in the right hand side less Km value to attain 1/2 of the Vmax. What does it means? The less Km means the substrate concentration requirement is less to attain the half velocity, which is good thing, no? So it reflects the enzymes and substrate affinity to each other, means Km is useful in term of rate of reaction measurements. High the Km means less will be the processivity of that enzyme to carry out that reaction. Low the Km means high the processivity of that enzyme to carry out that reaction, but Km is not sufficient alone. Here we have another term which is used for rate of reaction measurement, which is known as Kcat. So what is Kcat? Kcat is rate determining step in product formation process. So here we have seen that enzyme in association with substrate will result into the formation of enzyme substrate complex, and this complex will break down into the enzyme plus product. You know we have used rate constant. For formation of enzyme substrate complex we have used K1, and for dissociation of enzyme substrate complex we have used K-1 and K2. But here we are talking about product formation, so we will be focusing on K2 only because we are talking about product formation. So K2 is nothing but the Kcat in this case. Kcat value should be high in order to achieve more product formation. So it is an expression of turnover number. What is turnover number? The turnover number indicates how efficiently that enzyme produces that product. So the high K2 value or high Kcat value means high the efficient that enzyme. So we have two terms here. First we have seen Km and second we have seen Kcat. So an enzyme which shows high ratio of Kcat by Km, the high ratio means good enzyme. To understand this, let's see an example. Here we have written Kcat divided by Km. Suppose Kcat value is 10 and Km value is 2. The answer will be 5. And if you write in opposite manner, Kcat value 2 and Km value 10, the answer will be 0.2. So we are expecting the high ratio. So the first case indicates that this enzyme is good because it is showing high Kcat to Km ratio. So the Kcat divided by Km is the measurement of efficiency of any enzyme. So at the end of the day, if you noticed or remember that Kcat value should be high and Km value should be as low as possible, means the Kcat indicates the conversion of enzyme substrate complex into the enzyme and product separate, and Km indicates the requirement of substrate concentration to achieve the half the Vmax, means immediate enzyme substrate complex formation has taken place because of high affinity between enzyme and substrate. For that, less substrate is required. So the good enzyme is that enzyme which shows high Kcat value and low Km value. These are the very essential things you need to remember, and many times in CSIR-NET-JRF exams or other competitive exams, these are the concepts on which questions are based.
So friends, many steps we have seen here. We have seen how Michaelis Menten equation can be solved, and each step on that equation is very essential and you should know the basic reason behind each step. So we have seen the significance of Km and Kcat value, how these values are useful to explain the affinity between enzyme and substrate and how it affects on the rate of reaction also. But friends, this is not an end of the enzyme kinetics, this is just a beginning. So in upcoming lecture we will be studying on the basis of Michaelis Menten equation, Line-Muir-Burke plot and other equations and other inhibitor plots, how they can be plotted against enzyme and substrate. So I think this video must be helpful for you. So I would request you to please subscribe my channel and please share this video. We will meet in fourth part of lecture number 8. See you soon. Thank you.